Hi, my name is Paul Abernathy, and I'm the founder of Master the NEC as well as Master Electrician TV. On today's episode, we're going to do an inspection of this electrical cabinet inside of a single-family dwelling. We're going to look at the panel board, main breaker, the grounding electrode system, the grounding conductors, the equipment grounding conductors. We're going to look at the panel cover. We're going to look at legends, directories, all of the things that are associated with an electrical inspection, whether or not you're a home inspector, and we'll call out those things that the home inspector should look for, as well as a municipal inspector for any city jurisdiction who might be doing an electrical rough-in or a final inspection. So we're going to try to call out all those things that are associated with it during this video, and so stay tuned as we do a full electrical inspection on this electrical panel. Okay. Now we've got to the point where we're going to start looking at this electrical panel. The first thing we want to remember is that we have to have adequate working clearance here to work on this panel. Now, whether you're an electrician, electrical inspector, or a municipal inspector, or a home inspector, your client also as a home inspector needs to make sure that they maintain this nice clear space to get access to this panel. Now, all of these breakers are required to be readily accessible, so we have to make sure that we have good space here. Now, the National Electrical Code does give us some guidance on that. If you look at section 110.26A1, 2, and 3, you're going to find the requirements to maintain this safe working space. Now, the clearances that are involved in the National Electrical Code is generally the width. Now, the width is going to be, this panel, for example, is designed to fit between the stud framing members. So, you want to make sure that it's a 30 inches of clearance, left or right, for this panel to be in. Now, it doesn't matter whether it's to the left or to the right or in the center of those 30 inches. We want to have at least 30 inches or the width of the panel. In this case, the 30 inches is going to be the maximum for this size panel. So anywhere in here is what you're going to have allowance for that 30 inches. The next thing that you want to have is you want to have adequate working space in front of this enclosure. You don't want boxes, any tables in front of this, because we need to make sure that we can get to this very quickly without climbing over anything. So in this case here, we want to make sure that we have at least 36 inches or 3 feet. Now, the National Electrical Code will say 0 up to 150 volts, nominal 120 to ground, that you need to have 3 feet of clearance. Of course, if it's 150 to 600 volts to ground, it can go between 3 feet all the way up to 4 feet of clearance, depending if you're in a commercial environment, and also depends on certain types of conditions, whether or not you have conductive material opposite of this panel or live parts and what have you. So the depth can change here as far as your clearance is here. Now, what about the working height? We want to make sure it's at least 6.5 feet or to the height of the equipment, whichever is greater, that we want to maintain that clearance here so that you can actually get in here without ducking down and doing anything like that. Now, there are some exceptions for existing dwellings that have services that are 200 amps or less. Then you can have some reduced clearances, and that's something that you might run into as a home inspector on an older home that's not going to have the adequate height that you had for new codes. But you have to look at that, and that's something that you might want to look at in 110.26. There's an exception for that reduction of clearance. But right now we're looking at it from a municipal standpoint and a home inspector on a home. This home happens to be constructed in 2009, so these working clearances would be correct for today. So again, 30 inches, 3 feet out, 6.5 feet high or to the height of the equipment. This panel sits kind of low. There isn't any height requirement in terms of how low it can be. We do have some height requirements on the center of the circuit breakers, and it can't be higher than 6'7" to the center throw on the circuit breakers. But really, we're talking about the clearances right now. We haven't really gotten into any of those aspects. So once we've done that, we make sure we have good working clearance. The next thing we want to do is we want to look and see what our legend here, or this in case a directory, will tell us about this panel and about these circuits. So we want to look in here first and see what we can learn from this for our inspection report. If you're a municipal inspector and you're doing the final inspection, this directory is going to tell you a lot of things, because the National Electrical Code says that it has to be very descriptive and tell you exactly the circuit in detail. So we're going to look at all that, and we'll call out those aspects of it too. So that's the next thing we're going to do. We're going to jump over and look at this panel's directory. Okay, so now that we look at this panel cover's legend here. We start at the top. We kind of look right here. We have a little diagram right here. Now, this diagram is something that the homeowner can use to explain to their client how do you properly reset a circuit breaker. Now again, if you notice that it is tripped, then you move it totally in the off position and then you turn it back on at that point. Again, so this is a good little diagram to explain. As an electrician, we used to get calls all the time. People would say, my breaker tripped, how do I reset it? Well, obviously they tripped for a reason, so we need to solve that issue. But it might have been something logical that they had on in a bathroom or something that they, in a receptacle somewhere, that they overloaded it and it tripped and they just needed to reset it. It's their panel, they have the right, so I'd rather teach them how to do it first. And so this is a good way to show them how they do it, and it's a good diagram that explains that. All right. So now as we go down this legend here, this is our directory, we're going to look at some of the items here. So let me kind of scroll us down a little bit here if I can. And let's see what we can do here. Let's see what this information provides for us. Okay, let's stop right there. All right, so we're going to zoom in here a little if we can. And this information right here is going to tell us this is the model of the panel, which is a QOC40UF, which tells us that this is a 40 circuit panel. We can also look at the numbering on the cover here. We see that there's 40 circuits here. Also, when we look at it here, this is a type 1 enclosure. Okay, so this cabinet is actually, together with the cover, is a NEMA type 1 enclosure, dry location application, and of course that's where it's at, so that's important if it's installed in a wet location. And here it says it's a type 1, you know that that's a dry location. Also down here it tells you the model number for the main breaker filler plate, if you had to fill this plate here at the top for the main breaker, if this was being used as a somebody had knocked out the actual tab on it, you're using it as a main lug only. It tells you the type of filler that you would need for it. It has all that. It has a door lock kit number on here. Here's the other one here. This one here, you see it. This actually tells you the cover screws. So there's a kit that you can buy, and it tells you the model number, and these are the type blunt screws that go for this panel cover. Okay, so you get a lot of information here. Also from here, we're also able to tell that this is actually a square D panel. So if you put that on your inspection report to let you know that it's actually a square D. And this also again tells us that this type of breakers that go into this panel are a QO model. Okay, so this is what we got with that. So let's scroll on down a little bit here. And let's see what we got. Let's start out at the top. We have, let's zoom back out here. If you can get enough, you can see it. We'll kind of go down it. Here it says AC unit. Okay, this is going to be our AC unit. We look over at the panel. We see this is a 50 amp breaker for this right here. So this is our AC unit. That's probably our air handler unit. Then we come over here and we've got some other heating units that have to go with our HVAC unit. Okay, so what you want to do is you want to start looking down this legend here, and I'm going to try to zoom out even more if I can so you can see more of the legend here. So as we go down this legend, we're looking for descriptors. We're looking for things that actually describe the circuit that's associated with it. So that's important. So here we got a range, we have a dryer. Yes, they spelled dryer wrong, all good. Water heater. We're correlating it with the breaker. So we look over at the breaker and we see that we're dealing with a 30 amp for the water heater. So remember that when we're looking at the conductor size. The heaters, we're looking at a 30 amp for that unit. Here's a 60 for this, so we want to make sure the conductors correspond when we look into it. AC again is a 50, range is a 40, dryer is a 30, and of course then you have all these other circuit breakers that are associated here. Remember, these are 20 amp here, these are 15 amps here. When we look at them, we want to make sure the conductors that are terminated on them are the right size for this type of circuit breaker and their rating. But in this directory here, we want to look for descriptive things. For example, if it says master bedroom, that one's pretty easy because there's probably only one master. In this house, there's only one master. But the other ones say all bedrooms, lighting, bedrooms, receptacles. they need to be more descriptive on which bedroom we're talking about. If it says Susie's bedroom here, then we have a problem because Susie might not live here anymore. Obviously, if it's getting a home inspection, Susie's probably gone. If we're getting a municipal inspection, and this is the final part of it, nobody's even moved in yet, so how could they know it was Susie? So it needs to be more descriptive than that. It needs to be very clear, and 408 gives us that direction when we requirements to have the directory very distinctively clear on what it serves. Here you have GFCI plugs. This is the bathroom. We have refrigerator, dining room. Then you have kitchen GFCI plugs. And close enough, we know what they're talking about. Microwave circuit. Kind of want to make sure that all these breakers correspond. Okay. On this side, you have, it seems to be all the 15 amp loads, and this side seems to be the 20 amp loads. So we'll verify this in this panel. All of this process, we're still trying to determine the size of this service, and we haven't really got there yet. We haven't even pulled the panel cover off. But we're looking down here now. If I see any breaker over here that's not reflected over here, then I'm going to call that out. If I have something that's missing, the directory's not filled out for a specific breaker over here, I'm going to call that out. Again, I will point out that I'm using a non-conductive probe. In my case, I like to use paintbrushes. I have different sizes depending on the size of service so I can get in there. But it's a non-conductive probe. It's not metal. It's plastic, and sometimes they're fiberglass, and sometimes they're even just a plastic material. All right, so, or wood. All right, so here we go, and we're looking down here, and everything looks in order. One of the things we kind of look for is to make sure that it corresponds with the size, so we know that the kitchen is a 20 amp breaker, so that looks like they're good with that. So far, microwave at 20, looks like it's dedicated on its own. Here's a disposal and dishwasher, obviously being put on a 20 here. And you got the washing machine. So everything in here looks okay as far as how we look at the legend. Now in this case, this legend is detailed enough that I know which circuit breaker is associated with this different number that's on this actual cover. So that part we're okay. So the next step is to look at these breakers. Now one thing I'm going to also do before I take this cover off is to make sure that all of these breakers seem to fit well in this cover. Making sure that they're all seated, that there's none really loose, anything flopping around. Obviously I'm looking and seeing none that are tripped in here, those type of things. They're all on, so remember, it's hard to do a home inspection if the breakers are off. And so in your pre-inspection agreement, you want to make sure you make it clear that all of the circuit breakers are turned on for everything that you intend to check as a home inspector. So you're just kind of making sure everything looks in order. None of the breakers are damaged, cracked, any signs of deformation in the plastic. Anything that's going to stand out of the ordinary, you want to look at. And so everything looks good here. All the breakers seem to be seated pretty good. So the main breaker's seated well. So there's really nothing else in here that I'm too overly concerned with. The legend looks, the directory, I guess, looks pretty good in this panel cover. So we're going to move on from here and actually remove this cover. So we're pretty good. We've got all of our details here. Okay. So we're gonna close it. And now we're going to remove this cover. Okay. Now, we've already worried about our working clearance. We've looked at the actual directory. We've got all that information in place. Now what we're going to do is we're going to remove this cover. Now, there's a method to removing a cover, and we're going to use the cover for what's intended. Not only is it to help hold the breakers in and to help keep the exposure to all live parts, if there's any incident that takes place, it's going to help protect it from getting out. But now we're going to actually use this cover as a blast shield as we remove it during the inspection process. Now, the one thing we're going to do before we do that is we want to make sure before we do it that it's not energized. So we're going to use the back of our hand that is furthest from our heart, and we're going to check all the screws, run it along the cover to see if anything's hot or energized, that we might feel anything that's out of the normal. We can use a voltage ticker as well to test the screws, test the panel. Or again, we could use the old electrician's cheat method and use an extension cord with the prongs removed. The only thing you have is the equipment ground terminal on the extension cord so that you can plug it in a receptacle. You can bring it over here. You can take a voltmeter, put one end down in the slot for the equipment grounding conductor and take the other end of the voltmeter and actually test your screws and your panel and your hinges and everything like that using a voltmeter if you want to be sure. And then you're sure that this is totally not energized and it's ready to go. So now we're going to remove this cover. All right, so we get our screwdriver out and we're going to start, and I'm going to remove these screws in a specific order. Now again, it's going to be different depending on the type of enclosure and the number of screws that you're dealing with. But in this panel here, we got 6 screws, and there's a specific order that I'm going to remove them in. Okay, so the first thing I'm going to do, I'm right-handed, is I'm going to come over here and I'm going to remove these screws in successive order, and then I'm going to go over to the other side. So let's remove these. One out. You can use a power screwdriver if you want. If you're using a wiggy type screwdriver, be careful. It could be tight. You could slip off and you could actually scuff up your client's wall if you're a home inspector, and you don't want to do that. So again, I'm pressing my shoulder against this panel and keeping it there while I remove the screws. Okay, so I removed this side. I'm going to take these screws here. I'm going to look at them and see if I see any signs of arcing on them, anything that looks out of the ordinary. And of course, these screws are a blunt tip screw that's designed to go with this panel enclosure, so we're good there. Put them in your pocket. Support this panel cover and then shift over, keeping your hand against it to support it. Now put your shoulder against it on this side and remove the screws on this side. Okay. Now, I'm not going to remove the middle one, but I don't want the cover to slide down and potentially scuff up the wall. Okay, that's what we want to keep in mind. Again, this is some client's house, and if you're a municipal inspector, you're doing a final inspection, this is somebody's property, they're getting ready to turn it over or sell it, or it might be a home that somebody's built. You want to make sure you leave it in the order that it was when you first opened it. So everything's good here. Now I'm going to go down to the bottom screw, take it out. The last thing I want to do is damage up somebody's home. That's not what we're here to do. So, all right, so now we're down to this last screw. I'm still supporting it with my shoulder, my weight against it, kind of keeping it tight. The other little tip I'll give you is sometimes they paint all the way up to these panel covers. You can take a utility knife and at an angle, you can just score it along the panel, and you score it around it. You're not cutting into the actual gypsum board or whatever plaster, whatever type of wall material it is. But you're just kind of scoring it here in order to separate it from any paint. What I don't want to do when I remove this cover is potentially pull off any paint or any wallpaper or anything like that. I want to leave it again the way it was when I did the inspection. Now, last screws right here. I did it here because if I did it down here, there's always a chance in my movements that the panel cover could slip down. We don't want that. So I've got it secured. I'm right here, and now I'm going to take out the last one. All right, so the last screw is removed. I put that in my pocket. I get rid of that screwdriver. Supporting this panel cover. Now I'm going to start from the bottom, grip it, and when you push on the top, a lot of times the actual cover will pop out a little bit on the bottom that you can get your fingers under. Now, a couple things about safety. Okay, safety glasses, and if you're really worried, you already checked the panel, but if you're concerned, you can use gloves. Just make sure they're the right type of gloves. In other words, not too baggy, that you actually have no feel, because you don't want to lose hold of this panel cover and have it fall down, slip down, and damage it, scuff up the wall, come down and hit the breakers, maybe break a breaker or anything like that. You want to make sure that you can actually hold it. So, you can use gloves if you want. I typically don't because I get more feel, and I've already done all the safety precautions to check this panel. Now I'm going to use it as a blast shield as I remove it. So there's an actual way to remove the cover. This door is shut. I grab it at the bottom, I support the weight, then I grab the top. Then what I'm going to do here is pull it straight off. And I pull it straight off, and then I pull it away so that I'm actually protecting myself from anything that might happen in this panel. All right? So now we expose the panel. So the next step is to do a detailed inspection of all the components that are in this panel. And we're going to do that next. Okay. Now that we remove this cover, we're going to kind of do a little overview of the components that are associated with the electrical system to kind of give you, the home inspector, a little bit more understanding of what we're dealing with. So this whole cabinet here is called a cabinet, and it is governed by 312 of the National Electrical Code. This is a main breaker that's covered under Article 240 of the National Electrical Code for overcurrent protected devices. It is serving as protection to these conductors only from overload. It doesn't provide any short circuit ground fault protection. It's just simply overload protection. Okay, so the conductors coming in are these service entrance conductors coming in, and that's only providing overload protection, not any other protection. Now, from this point down, all of the components down here are being protected by this overcurrent protective device. And again, overcurrents protect you against short circuit, ground faults, and overloads. Okay, so these conductors aren't protected except for the overload. Everything down here in the panel board itself, which is this component, this is actually the panel board. The whole thing is a cabinet with the panel board, or the guts as we call it, inside of it. Okay, so here are your lugs, and these here are Allen wrench lugs or mechanical lug. This is a 2-pole circuit breaker or a double pole. This has to happen to have a single switch on it, but some of them might have two, what's called an identified handle tie in it. That's what you get from here. This right here is the neutral conductor or the grounded conductor. Here, these are called ungrounded conductors, and we know that this is a 120 240 volt system. We see the 3 conductors coming in, and this happens to be outside when it comes up to the meter. This is a service lateral. And so we have an ungrounded conductor, and we have what's called a grounded conductor. In this case, it's neutral. And it is neutral because it is neutral to each one of these legs. So from here to here is 240 volts. From here to here, it is 120 volts. And those, of course, are nominal voltages. Now this bus here, as it comes across here and down here, this is all one common bar or bus that connects the grounded conductors and the equipment grounded conductors together with the grounded conductor. Now this little green screw right here, and it's going to be green after 1990. If it's before 1990, it very well could be another color. So you need to look at that panel really closely and to see whether or not this main bonding jumper is actually installed. But in this case, it is of the green finish, which did come after 1990. So that tells us that this connects this cabinet, metal cabinet, to this actual bus that connects it directly to the grounded conductor. In this case, it's also a neutral application. These breakers right here are called AFCI breakers. They're going to be, and this panel was installed in 2009, but AFCI breakers have been around, that's arc fault circuit interrupter, have been around since 1999 requirements. Okay, it started out in the bedroom receptacles and it moved on to all the other outlets. And as you can see in 210.12a of the National Electrical Code, it has expanded greatly in the areas of the home that those circuits have to be protected for those certain areas. So these happen to be a combination. Now, a little bit of a lesson on the combination. What is that? A combination is not a combination AFCI and a GFCI. Okay, that is a dual function device. So let's clear that up right away. Basically, what combination is it detects combination, parallel, and series arcing events. So a parallel condition might be 2 conductors that are side by side that have an arc because of damage between them, an extension cord, what have you, that gets caught in the door in your house, somebody's running it through a jam or whatnot. There is no limit on the load here. It is simply an arc between conductors. The other one it looks for is called a series arc. And that is where you have a loose connection, and it's loose where it's just barely connected, and you put a load on the system because it's very load dependent. You plug something into the circuit and it creates a load through the system, and then it creates an arc right here. And this arc can rise in heat over time and to the point where it can cause pyrolyzation of material and cause a fire. So this little series arc is what's being detected by a combination. So it's the parallels and the series that are being detected. It is not considered, the combination is not an AFCI, GFCI. That is a dual function device. And they are available. You can get dual function AFCI, GFCI devices. It has both the protection of a GFCI, which is a Class A type of protection, which is 5 milliamps nominal protection. And then of course you get the AFCI protection that is afforded by UL 1699. Again, deals with parallel and series arcs. All right, so you have that, and it started back in 1999, and it expanded further on. You can get more details on that by going to the National Electrical Code and looking in 210.12a, and of course you also now have B, and you can look at some areas for when you're doing remodeling and when you've got to add AFCI devices and what have you. So that's what these devices, in this case we know that these are on the bedroom, okay? So based on the time period of this home, we're going to look in the actual directory and we're going to see that they correspond here. All right. So we're looking at that, and these are single pole breakers. These are 2-pole breakers. And another thing we're starting to look at is the conductors. Okay. So we'll look at all the conductors, and we'll do that during our inspection of the actual components here. But we wanted to point out some things in here This is non-metallic sheath cable, and actually they left the actual sheeting on here. Some people have a concern with that because they say it's combustible material within the enclosure. I have no problem with it because I know that there's fire retardant properties inside of this non-metallic sheath cable because it is installed in a dwelling, and that is a requirement of the standard for non-metallic sheath cable, which is UL 719. So I don't have a problem with that. Some people say there's paper inside of it. Whatever, you know, do what you want to do. It's obviously easy to remove if you want it. I don't concern myself on that. In fact, I like that it actually adds some added protection to the individual electrical wires that are inside of that cable. Okay, so that adds that protection for there. So basically that's what you're looking for here, and those are the basic components. So again, this is the panel board, the main breaker. These are terminal lugs, mechanical lugs. This is ungrounded conductor. This is your grounded conductor, also serving as a neutral in this case. This is a cabinet with a panel board in it. We saw the cover earlier. Also could be called an enclosure, if you will. There's no other issues with that. So with that said, let's go on and dissect this panel from the very beginning, both how a municipal inspector would look at it and how a home inspector would look at it. All right, so let's start looking at this panel and seeing what we can notice here. The first thing I'm going to do as a municipal inspector, let's say it's a rough-in. If this panel is installed in a rough-in and I'm a municipal inspector, the first thing I'm going to look at and see, is this material around it actual combustible or not? And here it's a gypsum board or drywall, however you want to call it, and it is non-combustible. So that I know that this enclosure can be installed at up to 1/4 of an inch back into the wall, okay, recessed into the wall. Now that's in accordance with 312.3 of the National Electrical Code. Now, if this was a combustible material like wood, then it'd have to be flush. Okay, this panel would have to be flush. Okay, we don't want any embers to get around the side of it and get into the combustible material, which brings us to the next thing. If you're also doing a municipal inspection, you're not going to tell this on a rough-in, but you will on the final. You want to make sure that the gap around this panel does not exceed 1/8 of an inch. Now, home inspectors, again, you also want to make sure this panel, if it is a non-combustible material, that it's not more than 1/4 of an inch deep in here, because there are some things that we can do to correct that. We also want to make sure that this gap around it, in accordance with 312.4, is not more than 1/8 of an inch around it, which is very common when somebody does a flip or remodel, or they did a change out and they trimmed it very poorly around it and you got these big gaps. The last thing we want is to have an arc and an ember get over in between this material and smolder down in between this combustible material, the wood framing that's behind here. So we want to look for those type of things. So again, that's 312.3 and 312.4 of the National Electrical Code. Okay, the next thing we want to do is, the first thing I like to do is to start with how it comes in. So here it comes in through it appears to be a non-metallic nipple back to back with the meter that's on the outside. So one thing I noticed that these conductors are obviously larger than a 4 gauge. So in accordance with 300.4G of the National Electrical Code, any conductor that is 4 gauge or larger would have to have a bushing on the actual raceway as it comes in order to protect these conductors from being cut on this sharp edge here. And I do notice here that this conductor right here, this wire, looks like it's cutting into this actual insulation right here as it comes in. The good news is this is non-metallic. If it had been a metal one, we have even a bigger concern. But it is non-metallic. But you are required to have a bushing on all raceways in accordance with 300.4G of the National Electrical Code. So we have to establish that. Now, municipal guys, you're going to check this on the rough end. You're going to make sure that they do that. Again, all right. Now, if this happened to be a metal nipple, then you're going to make sure you bond this nipple. You have to do it in accordance with the National Electrical Code in order to bond it at least on one end. Now, I can't see in the meter, so in this end, I would have a bonding bushing here, and I would have to make that connection here in order to bond this side in accordance with the service bonding and a surety aspect of it. Okay, so in this case, it's PVC. I do need a bushing on it that's just to protect from damage that it comes in, so that adds that extra level of protection here. Now, as a municipal guy, if I see some damage in here, I'm probably going to call that out. If I don't see any damage and everything looks good and it's not bent too much, then I might not call it out, because that's they have to take all this loose in order to do that. And again, unless they pull the meter, these are energized parts right here. These are live. So when you pulled it loose, it could be a little hairy, and I don't want any homeowner to think they can do that. So call this out as you see it. Again, that's a violation of 300.4G of the National Electrical Code. Now, I'm going to look at all these individual conductors here, all these wires, and I'm going to look for anything that looks like evidence of damage Anything that looks like it's scorching, anything that looks where they actually, when they stripped it out of the actual cable, that they damaged any of it, cut into any of it. I'm going to look at all those aspects, and I'm kind of going to give it a visual around it. I've looked at this one, and I don't see any damage anywhere. None of the colors look defaded out, or none of the insulation looks damaged or anything like that. And when I say faded out, sometimes when you strip it and they accidentally do it with a knife, you'll see some areas that look faded out in color, and that's because they stripped off the color, the outer color. So I'm looking for those type of things. I don't see anything with that. So everything looks good. No damage there. All right, the next thing I'm going to notice is if I'm a municipal inspector, I'm going to notice that they bought all of the actual non-metallic sheath cables and SE, which is service entrance cable type U, which is what this is. They bought it into the actual panel cabinet, and they did it through one single knockout. Now, they did put a bushing here, but the problem is this isn't permitted. Okay, so the National Electrical Code says in 312.5C, says that all cables that come to a cabinet have to be secured at the cabinet. Okay, well here they're not secured. There's a whole bundle of them is bought in. Now, there is an exception to this rule, and if this was a surface mount cabinet and there had a raceway that these cables came into was at least 18 inches long and no more than 10 feet, and all those cables were secured within 12 inches of exiting that raceway, and it was sealed at the end, then I can get away with that, although I do have to worry about bundling issues, and we do have allowances in the code that deals with that. But in this case, municipal inspector, I'm going to call this out because this is a violation of 312.5C. And for a home inspector, we don't know what's in this wall. We do know this is a violation. Okay, we don't know what's in this wall. We have to know the age of the panel when this might have been prohibited under 312.5C. So we might have to do a little research on that. But again, these cables here aren't allowed to dissipate heat. They're bundled together. And the good news is this is a residence, so there is a lot of diversification. So the one thing that we could do is we could take our infrared thermometers here and we could shoot it in here in some of the cables, some of the conductors, and see if we get any evidence of elevated heat in here, just as a precaution. Look in here and then see around the cabinet, do we see anything? And here everything's about 78. And this is in the morning in Texas, so that's about right for about 10 o'clock in the morning here. Everything looks good. I don't see anything. But again, as an inspector, municipal violation. Home inspector, call it out because you don't want somebody later to have a problem in this wall because of this issue right here and somebody tell you you missed it. So you want to call it out, but you're not going to flame it. You're going to let the electrician determine whether or not it's okay and let them be on the hook for that. Defer their liability to them. Okay, but this is might be acceptable in your jurisdiction. They might have allowed something like this. Again, but the National Electrical Code does not permit this application. All right, it does with an exception, but not in this case. All right, so I'm looking at all these conductors and everything looks good. So I get down to these conductors here. And as we said earlier, these are your ungrounded conductors, or referred to as a hot. And this is your neutral or grounded conductor. Now, in a 122 40 volt application for a one family dwelling like we're dealing here, a single family dwelling, or 1 and 2 family dwellings, then this is a 122 40 volt application. Then what we're going to notice is we've got only 3 conductors coming in. So that tells us that we have a 122 40 volt application. Also, we'll find that on this legend over here in a little bit as well. But now we need to size these conductors and make sure they're the right size. Now these terminals are based on 75 degrees C, as the legend over here is going to tell us, and we'll see that in a little bit. So we know that these conductors right here have to be at least 75 degree rated insulation, and that's pretty typical for the building industry today. In fact, they're probably all going to be rated 90 degrees C, but that's for adjustment and corrections. We are going to be limited to the terminals. So these terminals are at 75 degrees C. Now, just so I happen to see right here, and you won't always get this lucky, on this grounded conductor, which is the same size here, it says a 2-aught AWG. Okay, so I happen to know that these are also 2-aught because you can actually see the writing right here on the side. It says 2-aught right here. And I know that in accordance with 310.15b7 of the National Electrical Code that says if this panel handles 100% of the load, then I can use that reduced ampacity table for the sizing of these conductors. For example, under 310.15b7 of the National Electrical Code, if this panel handles 100% of the load, then I can use that table, and basically these conductors have to be at least the ampacity value of 83% of the rating here, and this is a 200 amp rating right here. So these have to be at least that. Now, if you had the old National Electrical Code back in 2008, you had a little table there, and that little table said that this 2-aught copper is good for 200 amps. Now, under 310.15b16, which is your normal ampacity table, you're going to see that it's not. It says it's good for 175 amps. So that's how you're able to use it, that smaller table or that calculation now, to determine the minimum size that you need for a 200 amp service. So that's how you would do it in this case right here. There's enough diversity inside of a residence. Not all things are on at the same time. The loads are always a little different. So that diversity allows you to use that table that allows a 2-aught, which is really only good for 175 amps, to be used on a 200 amp rated service because of that diversity. It's still okay. All right, not a problem. All right, so one thing we notice here as we're going around looking, everything looks good. The terminals look all right. There's no deterioration here, no discolor. Again, non-conductive probe. I'm looking in here. Everything looks pretty good. Everything looks good. Everything's tight. Not an issue with that. Again, your standards of practice might say not to poke things into the panel. I'm a licensed master electrician. I'm trying to do a video, so I'm going to show you with a non-conductive tool. I want to probe around a little bit. Here is a main bonding jumper. This main bonding jumper is required on service equipment. So I have to connect the grounded conductor and its associated bus bar to the actual metal cabinet, so that when I bring equipment grounding conductors in and my grounded conductors in, that they connect to the same common bar that's also connected to the enclosure. In case my enclosure gets energized, we want to have this equipment grounding conductor allow for fault current to come back, get to here, and get back to the grounded conductor to complete that cycle to allow these overcurrent devices to operate correctly. All right, so everything is connected together. The grounded conductors are connected to the bar, which is connected to the grounded conductor, which has a main bonding jumper connected to the metal enclosure. And of course, the grounded conductors over here are terminated. Okay, so now, if this was a remote distribution panel, because I get that question a lot. So let's say this is a panel that's out in your basement, a remote from this one. So we'll have a breaker here that feeds a panel downstream somewhere, or out to a detached structure, out to say it's a barn or what have you, out in your yard or whatever. Then that's going to be called a remote distribution panel. This panel could be used in that application. The one thing you would have to do is you have to remove this main bonding jumper. That isolates this bar from the metal enclosure when you remove this main bonding jumper. The next thing I would have to do is I would have to install a totally separate equipment grounding terminal bar on this cabinet. And here you see there are screws under here that tell you where and how to install that equipment grounding terminal bar inside of here. And this label over here is going to see, and we'll see this later, it's going to tell us the model number when we have to order the bar that goes inside of this actual cabinet. Okay, so that information is going to be found here, and we mount it right over here, and they're actually threaded screws here for mounting that bar in here. All right, so what you want on a remote distribution panel is you want the actual equipment grounding conductors connected to the cabinet and to your grounding electrode system. Whereas and you want your neutrals to be isolated away, kind of isolated off of the cabinet. In a service panel, that's totally different. You want it all to be the same. I want the cabinet connected to the bar by that main bonding jumper. My equipment grounding conductors terminate on the same bar. My grounding conductors terminate on the same bar, all together. Not the same in a remote distribution panel. Also, we want to make sure that our grounding electrode conductor, or our GEC, which is what's running down here, that's going out to a ground rod, and in this case, a UFR ground, we want to make sure that they connect to the grounded conductor. And that is told by 250.24a of the National Electrical Code that we have to do that. So that is done here. But remember, on a remote distribution panel, that grounding electric conductor does not connect to the grounded conductor. It connects to that separate equipment grounding conductor bar that you ran. Because on a remote distribution panel, you're going to need to run 4 conductors. 2 HOTS, a grounded conductor, and you're going to run an equipment grounding conductor. So you need 4 conductors at a remote distribution panel. Okay? For some of you home inspectors, early on when you get some old inspections to some old detached structures, you might see only 3 conductors run to it. That was prior to the requirements that are found in 250.32, which now requires that you run 4 conductors and a separate equipment grounded conductor and a separate grounded conductor out there, and you separate them when you get to that remote panel. Okay, so that's evolved over the years, so just keep that in mind if you're dealing with something that is an older type of detached structure. All right, so that's what we got here. This lug right here is actually where they would bring the grounding electroconductor to make that connection to the grounded conductor. But since this whole bus or this whole bar system is all considered one and it is connected to the grounded conductor, then as long as these lugs are sized large enough to take that 4-gauge copper in here or the 6-gauge copper, whatever it may be, then it's okay to terminate it here and not in here because it's all considered one. All right, and the number of the size of the conductors that terminate onto this bus or even these lugs are over here in this legend here. It tells you the maximum and minimum sizes that can go into the various lugs and terminals. So that's what's important about that over there. Okay, so as we come down, we see these equipment grounded conductors. We want to make sure that each one of these equipment grounded conductors are terminated in a screw, that none of them are loose. And what I like to do with non-conductive probe is I kind of move them down like this a little bit. And it's non-conductive, and I try to see if there's any of them that wiggle around or move. You know, I just do that, and again, whether or not your standard of practice allows you to do that, that's up to you. If you can do it from a visual inspection, you can see all that, you know, good for you, but we're going to try to show you some of the things that I would look for. So I'm looking, and if I'm a municipal guy, I'm going to come in here and make sure this one a rough end, that all of these are terminated and nothing's loose in here. Okay? Now, how many of these equipment grounded conductors can I have per terminal? Now, this panel has a directory right here again. It's just on the inside of the cabinet that's going to tell me that I can have up to 2 14s or 2 12s under the same terminal lug, or I could have up to 2 12 aluminums if I had aluminum branch circuits in here that could terminate under the same lug. Now, it doesn't tell me that I can terminate a 14 and a 12 under the same, but there is no way that it can actually torque properly on the 14 gauge if it's trying to also terminate onto a 12 gauge. It's just different sizes, so the torque cannot happen. So that's an issue. So we want to make sure that they're the same size. So in here, if I have 2 14s under this screw, their 2 14s are okay, or 2 12s are okay. All right, but I can't have a 14 and a 12 sharing it. All right. Now, as I move down over here to the grounded terminals, I want to make sure that I only have one grounded conductor per terminal. Now, that's in accordance with 408.41 of the National Electrical Code, but it goes really deeper than that. It also goes all the way back to 110.3b, which says that you have to install this panel in accordance with the instructions. And the UL 67, which is what governs this panel board and all this componentry that goes along with this panel board, that, remember, we're dealing with a cabinet here, and this is the panel board in the middle. It says under UL 67, it did not permit this. And so under 110.3b of the National Electrical Code says that you have to install this in accordance with the instructions. And the instructions on here, even the identification in this legend over here, says nothing about the multiple grounding conductors sharing a terminal. It does talk about it for the equipment ground, but it doesn't give you any permission to do it over here. So it was not allowed long before the National Electrical Code incorporated 408.41 into it. So there is your evidence of why these need to be under a single termination. The other aspect of that is if you terminate 2 of them under the same lug, if they were different sizes, then one wouldn't be making a good connection and create an arc. So it is a current carrying conductor, so you're going to have current traveling through it, and if it's loose, you're going to create an arc. Arcs produce heat over time. It starts to melt down the insulation, it raises up its temperature, and it can cause damage to it. It could come loose, and if it's a multi-wire branch circuit, you have an issue with the neutral coming loose, and that could be a problem because you turn what is 2 circuits that are 120 into 240 volt circuit, and that could damage things that are plugged into that multi-wire branch circuit application. So you want to make sure, we want to look and see if any of these are discolored. We want to see if any of them are grayed out because they could be on a multi-wire branch circuit and they don't have them properly aligned in the panel. It could cause these insulation to overheat, melt down, deform, and you want to notice any of those type of things. So look for any arcing, any deformation of the insulation, anything that looks out of the normal, anything that starts to look blackened or what have you, you want to actually call it out. And you have to do a little more investigation to see why that might be the case. And so I'm looking at it here, and here's our main breaker, again, off and on. It's in the on position. Now, again, if I'm doing an inspection, if it's a home inspector, I have to do an inspection on all the breakers that are on. I'm not going to turn any that are off on because they're obviously off for a reason. So, you know, I'm going to denote the fact that it's off and that I couldn't test that circuit. And if the legend matches up to it, then I'm able to actually do it that way and can actually point out which one it is. Obviously, it'll be clear because it's off, but you want to note that in your inspection report. All right, so then I'm kind of just looking here, and that's kind of all I'm looking for here. I'm looking for any damage, any cracks, any damage, any modifications to the bus, to the bar, anything that looks out of the ordinary. And I don't see anything that looks out of the ordinary. So in that, we're going to kind of move down a little bit, and we'll talk about the individual breakers as we move down a little bit. All right, we're going to move down to about right here. All right, again, these are considered two-pole breakers. These are considered single-pole breakers. Okay, this happens to be square D tends to have one lever on a two-pole, whereas some of them you might see two levers, and they have what's called an identified handle tie. It is listed to use with that breaker. It's identified for its application, and it can turn off both of the actual toggles onto the actual breaker itself. Now, we talked about earlier a multi-wire branch circuit. In case you're one of those home inspectors that run into multi-wire branch circuits, one thing to remember that as you go down this bar, it alternates. So this is being A and this being B. You have A, B, A, B, A, B, A, B, A, B, all the way down. So it alternates. Now, if I install this two single pole breakers for use in a multi-wire branch circuit, which the National Electrical Code permits me to do, and I use an identified handle tie to bring them together, then the one thing I want to be aware of is that there's an A leg and a B leg. Here, A, B. Okay? So what happens is if it's a multi-wire branch circuit, so it's like a 14-3 or a 12-3 where I have a red, a black, and a common white, and it's going out to two separate circuits, and they split off. Okay? Like bedroom A, bedroom B. All right, red goes to A, and then you have black goes to B. The neutral is going to be the common conductor that comes back. One, we want to make sure it's on its own lug. It's not ganged up with anybody, okay? And that's why we're looking for brownouts and things on the insulation that might have discolored, because we might have what's called an improper multi-wire branch circuit. So the proper way to do it is make sure that they are side by side with the handle tie. But let's go down to here. Let's say that I installed a multi-wire branch circuit, but I installed it improperly. So I put one breaker here, and I put the other breaker for the black conductor, red conductor, this one, and the black one over here. Again, that is on the same plane. That is on the same leg. That might be all A. So in a multi-wire branch circuit, if I've got 10 amps on A and I got 10 amps on B, then if it was properly installed, then I'm going to have 0 traveling on the neutral conductor, return conductor. There's a cancellation effect that takes place. But if I have both A leg and I have both the black and the red both on the A leg because they didn't use a two-pole breaker or two single poles with identified handle tie, then if I've got 10 amps traveling on A and 10 amps traveling on B, or which is still A, 10 amps on A and 10 amps on the other A because it's in the same line, then what ends up happening is I have 20 amps traveling on that neutral because there's no cancellation effect. So I've got 10 amps on the A, and because I'm installing it right across from it, I've got 10 amps on the other A, and that's 20, where it's supposed to be side by side. That way you ensure that it's equally distributed. I have 10 amps on the red one for the A, and 10 amps on the black one for the B, and it creates a cancellation effect, opposite points in the sinusoidal waveform. Really too detailed for this type of video, but what you get is you get return current as 0 on the neutral. Okay, and it also carries the imbalance. So if I have 10 on one and 5 on the other, then I have 5 of imbalanced current that's actually traveling back on the neutral conductor. Okay, so that's why you want to make sure it's two pole breakers with an identified handle tie, or two single pole breakers, identified handle tie. You want to make sure they're installed properly in the enclosure and not spread out and accidentally on the same leg, because that could be a problem. The current becomes cumulative at that point, and you will overload a neutral. And that's why we're looking up here for any discolorations. So that's one of the issues. Again, making sure these are all tight so that you don't get any arc when that load's coming through the circuit could cause a brownout and an arc out, and that could be a problem as well. All right, so that's what we look for down here. Now, another thing we're looking at, these are all square D breakers. If I happen to see another brand in here, one thing I have to realize that this panel recommends the use of square D products. However, they do make certain breakers out there that are called classified, that have been identified and evaluated for use in other type manufacturers' enclosures. Okay, So it doesn't void any warranty on a replacement because of the Magnuson-Moss Act. But in new installations, you want to use the breaker that's listed for use in this panel because that is part of the 110.3b for this manufacturer. Now, later on, if it's a replacement breaker, that's where that classified breaker comes in. But new installations, make sure it's the model that can actually go inside of this panel. These happen to be QOs from Square D, and every one of these are QOs. But if there happened to be a Siemens in here, if it happened to be a Cutler Hammer BR style, which wouldn't fit in a QO anyway, but they do make classified replacement QOs. Okay. Now, if this was a BR style or the home line version of Square D, then what you might have is you might have a Siemens or a GE or whatever in here. And again, that is not listed for use in this panel. Okay. It's a different manufacturer. Now, they do make a list out there that will let you know which breakers can be used in which enclosure and on which panel board. Okay, and I get Cutler Hammer and a couple of the other Thomas & Betts. All of those create what's called classified breakers, which have been evaluated for use in a specific manufacturer's enclosure and on their panel board and in their cabinet. So that's what you utilize that. And there's a list out there that you can get. In fact, we'll post it up on Master the NEC for you to be able to download if you'd like it. All right, so that we've looked in here, and all of these happen to be all Square D, so everything looks good here. Also down here, we have, again, some AFCI combinations. Again, that's combination for parallel and series. They are in good order. The other thing I want to talk to you about the test button. Now, the proper method to test an AFCI is by using this test button. You have little AFCI testers out there, but the reality is these are the buttons that I want to test it by. If I test this button right here, then I would go in and check that circuit, make sure it corresponds to the directory, make sure it actually does what it says it's going to do, and then I would reset it. So you do trip them and reset these. So I trip it all the way off and then back on, and that's what I'm going to do for these here. All right. So the next thing I want to do here is I want to actually look at these conductors that are actually terminated to these breakers. So what I'm going to do is you're going to look at all of these terminations here, and you're going to see if there's any damage to the conductor. And this is a good way to take a magnifying glass and actually hold it right here, and kind of gives a blown up version of all of these terminations. Again, people laugh at me about that, but again, a nice large magnifying glass. You know, they're going to call you Inspector Gadget. But again, it allows me to get a nice close-up view to see if there's any damage. Now, if these are aluminum conductors, again, there is absolutely nothing wrong with stranded aluminum. If I see some nicks on the copper or aluminum, I'm going to call that out because a nick creates a resistance point in the actual wire. And we don't want that because it could generate heat. So we want to make sure that it's been stripped properly and it's terminating. We're also going to look at all of these terminations. If we have two conductors on a terminal, that's called a double tap. We then have to look and see whether or not this breaker is designed to handle two conductors. No, not all breakers are designed. I know that in the QO brands that the 15 and 20, and they do make a double pole 30 that will accept two conductors on a what's called a saddleback type of termination. But you won't find that in the 40s or the 50s or even in the 60s. It's going to be on the lower ampacity rated overcurrent protected devices. If it says it, you can't see it because it'll be on the side, but you can tell by looking at the terminal. If it looks like a saddleback, then it's going to, which has two openings to allow two conductors to go in it, then you know that it's rated for two conductors. All right. If you don't see that, it's just a screw, then it's only rated for one conductor. All right. So that's part of its rating. So I'm going to look down here and see and make sure everything. Now, with my non-conductive tool, being honest with you, as a municipality, I actually do this and see how snug they are. You can do that if you want. You don't have to in a municipality, but I'm going to see how I'm doing it. And everything looks pretty snug. That one right there looks pretty good. All right, so the other thing you'll notice in here is these conductors. Now, this is a non-metallic sheath cable running. This happens to be a 30 amp, so I know these are 10 conductors. Here's a 30 amp, and now these are 10 conductors. I can tell by the size. But in a non-metallic sheath cable, typically you're going to have a black and a white. And see, the code requires that they re-identify the white in a cable for use as an ungrounded conductor, and that's acceptable. But they did here, they did just a Sharpie on it. Now the code says under 200.7 that I have to encircle it. So I have to actually wrap all the way around it. And here they just did some on top of it. So they didn't necessarily encircle it. As a home inspector, I'm not so worried about this because they actually did color it black. As a municipal inspector, I'm going to make them encircle this with tape or some other material to re-identify it. in order to let me know that this white is now being used as an ungrounded conductor. And they don't have to do that on the whole conductor here, on the whole wire. They just have to do it here at the termination so it identifies it and it's permanent. All right, so here, and there's a couple of those in here that they do that on. So here they happen to use the Sharpie. Again, as a home inspector, I'm not worried too much. They made the effort to mark these, so I'm going to kind of go with that. Municipal guy, if you're going in doing an inspection on a rough end, out of the final, you make sure that they put some tape around it. All right, so everything looks good down here. I don't see any issues with that. And I do the same on this side, and I look at all these terminals to make sure that they're all in good order. The next thing I want to do is use my IR. Now I'm going to zoom out a little bit so that I can show you what I do with my IR. Actually, it looks like we're in pretty good shape. All right, here's what I do. Okay, so how do I use this device in order to give me some baselines to tell whether or not potentially I have any overheating of these breakers, if there's any bus terminal that is loose that's generating heat. I'm going to get a baseline. So the first baseline that I like to do is I actually like to go to the actual cabinet itself. And this cabinet is 79 degrees. And it's mounted against a brick wall on the other side here. So it's about 79 degrees. The next thing I'm going to do is I'm going to shoot the actual lugs that my ungrounded conductors go to. And I'm going to shoot here, and I'm going to shoot inside the actual lug here. And this is about 79, 80, so it's about the same as the cabinet. Then I'm going to go over here and shoot the other. And this is about at 80. It's about the same as the cabinet. Then I'm going to shoot my grounded conductor. And it's about at 79. Okay? So that's my baseline. All right? So now, one thing I like to do is to shoot it on every one of the terminals for the grounded conductors. So I kind of just shoot them on here and move it down and kind of get a baseline. I want to see if I'm showing any loose connection or any heat that might be building up in here that I can't see. And it gets bought into the actual screw itself. And it looks like everything here is about the same. So again, what I'm looking for is any abnormality, anything that's not in the norm. Okay, so everything, so I've set my baseline, and now I'm going to come over here, and I actually do the equipment grounding conductors as well. I just do it to test and see. And again, all of these are about at 80. So everything looks good. Everything looks the same. Now, I'm going to do each one of these breakers terminals. And I'm also going to even shoot, in here you can actually see the actual terminal, the bus on the panel board. So I'm going to shoot it and see what I get here. And that should be about the same, so it's about 80. Then I'm going to shoot over here. And it's about 79.5 or 80. So I'm feeling pretty consistent here. Nothing out of the ordinary. The ambient in here, again, like I said, when I shoot the actual cabinet, it's about 80. So everything else looks pretty good. Now, I'm going to go down and shoot these terminals. Now, I'm going to start from the very top, and I'm going to move to each one. Okay? And what I've got here is I'm getting 79, 80, 80, 80, 80. And you're going to keep on going down every one of them. And you're going to go over here and do the same thing. Now, one thing you will notice different is these AFCIs. Now, the AFCIs tend to run about 10 degrees warmer. It can fluctuate a little bit. Again, they got circuitry in here that's going on. They generate some heat, but nowhere near anything to be worried about. So I'm going to shine it in here and see what I get. And that's a 90, 92, 90, and about 90. All right, so basically what I've got is this were 80 and these were 90. So it's roughly about 10 degrees. Again, if there's any load going on, then they might warm up and be a little warmer. But you're looking for drastic differences and understanding that under a load condition, the terminals are going to heat up. Again, we have 90 degree rated insulation, that's 90 degrees C, or 194 degree rated Fahrenheit for the overall rating. Now, we know that this is non-metallic sheath cable, so we are limited to the 60 degree rating on this in accordance with 334.80 of the National Electrical Code. And of course, the ampacity values for it are going to be in accordance with 31015B16 in the 60 degree column. All right, so that's what you're dealing with when you're dealing with non-metallic sheath cable. Now, these cables obviously up here, the service cables right here, These are actually at 75 degree for ampacity based on this terminal. Or in our case, we used, again, 31015B7 for that application. So I've done this. Now, the other thing I like to do when I've already got this out is I just kind of go around the other parts of the cabinet, just looking at it. 78, 78, 79, and then I got some open buses down here that I'm going to actually do, and just to see what I've got down here. 79, so about 80. So it's about 80. These are elevated about 10 degrees higher for the AFCIs. That's perfectly acceptable. I would expect the same thing if I had a GFCI device in here as well. Okay, so now the reason you don't see any GFCIs in here for like the bathroom receptacle and the garage receptacle is because they actually have GFCI devices in the receptacles that are in those locations, so they don't need to be here. All right, so everything we looked down there looks okay. So the next thing we want to look at is we want to look at our grounding electrode conductors. And let's do that here. So I'm going to actually pan down a little bit and we'll kind of get those there. Now I'm also going to zoom in a little bit in order to be able to get in and look right at these conductors. All right, now what I can't show you is because the owner has a boat in the way, and I actually got over there and looked at it. But there is what's called a U for ground, or a concrete encased electrode ground here on this dwelling, which in this case they ran a 4-gauge copper to that location, which is in accordance with 250.66, and you have an A, a B, and a C, which gives you some allowances for ground rings, concrete encased electrodes, and ground rods, plates, and pipe electrodes. We have some allowances there, and so for a U for ground, or a concrete encased electrode, it doesn't have to be any larger than a 4-gauge, in this case copper, 4-gauge of copper. All right, so that's what they ran. They chose to run copper to that. Now, I could run aluminum to that. As long as it's not terminated within 18 inches of the actual earth, then I could run aluminum for that, believe it or not. But here we're running copper, so we'll stick with the copper. And so this was a 4. Now that is the adequate size that you would run to a concrete encased electrode. Now if it was to a water pipe, for example, then you're going to have to use the sizing that's in 250.66 in the table. Okay, so we have some allowances for those certain types of electrodes, but if it's a water pipe, structural steel, those type of things, then you're actually going to use the table itself, or you can use 250.66 A, B, or C if you have those type of electrodes available. So in this case, it was a concrete encased electrode, so they ran a 4. And they're acceptable for that. Now remember, this grounding electrode conductor has to terminate to the grounded conductor, and it terminates up here on the bus that is in intimate contact with the grounded conductor. Or it could actually have terminated into that lug that's right next to the grounded conductor. That would have been acceptable as well. Now, the other one they happen to run here, and I know it because I've seen it, and we'll look at it here in a second, is they actually ran it to a ground rod. Okay, so now the ground rod, the code says in 250.66A that it doesn't have to be larger than a 6. Because to be honest with you, that's all that a ground rod can handle. If it's driven 8 feet into the ground, if you can't drive it, then you're allowed to do it at a 45-degree angle. If that doesn't work, then you have to dig a trench 2.5 feet down, and then you're going to actually put it in that trench. Okay, so, but you have to make sure that if you have multiple electrodes out there, that they're at least 6 feet apart, and we'll look at that when we get out there. All right, so anyway, we've got this application here. And they chose to use a 4-gauge copper solid as well for that electrode outside the ground rod. They only needed a 6, but in this case they used a 4, probably all they had. So that was acceptable. Yes, it can be larger, provided that the lug that's on the actual electrode can handle the larger size conductor. Very frequently we have engineers who will go as high as a 4/0 to a ground rod, and we don't understand why they do that, except for sometimes they believe it's more important around towers and things like that. But the reality is a ground rod can only handle so much. Okay, so you can go as large as you want, but the code doesn't require it to be any larger than a 6-gauge. Okay, so here they are. So now let's look down a little further, and we're going to see how they actually go through this cabinet. All right, so here we are at the bottom. And they actually go through this little opening right here. Now, here's the misconception that people have. This is not a weep hole. This is a NEMA Type 1 enclosure, okay? This isn't a weep hole. This isn't a NEMA 3R. this opening here, these little knockouts that are either side of the main knockout here, are designed to bring the grounding electroconductors through. In this case, they bought 2 of them through the one opening. As a home inspector, I'm not too awful concerned with that. They have 2 of them here, so they could have come through this one as well. But they didn't. They bought 2 of them, and it doesn't look like any damage on here. You kind of look at it. And so that's what this is designed for. And there's one on either side. Now, if they bought it through a knockout, let's say this is a 1/2 inch knockout, and they bought it in and they didn't put a connector on it and it's just loose in there, then we want to call that out because it moves back and forth. Also, if it's ever used, maybe in a lightning strike application or something where that's you're using this grounding electroconductor, it could create an arc over here, and it kind of could inhibit its use. It could create like a choke effect. And what happens is it kind of starts to decrease the effectiveness of that grounding electroconductor. We don't even want to speculate on that, so we want it to be secured to this enclosure. They do make a special clamp called a Kinney clamp that can do that. A lot of times you'll see a non-metallic sheath cable clamp here, and they run this through that. Look, if it's in a new installation, then I might not like that, and I might say use this hole, it's designed for it, or use a special Kinney clamp. As a municipal inspector, I can call that type of stuff out. As a home inspector, as long as it's coming through here and it has a connector on it and it holds it in place, that'd be more of my concern, is to make sure that it's not just in an open knockout, because it has to have a connector on it. Here, these holes were designed for it. Here, it wasn't designed for it. Okay. Like I said, they do make special clamps that you can use to hold the GEC as it comes through the actual cabinet. All right, so that's what I'm looking at. Now, I'm also looking to see if I see any deterioration, any moisture, any evidence of leaks, anything like that, any scorch marks. Everything looks good. We've already looked over this enclosure. I really don't see anything. We've actually looked at the gaps here to make sure that they're not more than 1/8 of an inch, that the panel's set flush. If it's combustible, if it's non-combustible, it can go back 1/4 of an inch. We've talked about multi-wire branch circuits and the breaker configuration. We talked about AFCIs. We talked about the conductors a little bit. So now let's kind of look at the sizing of these conductors. All right, so this is a 50 amp device. Okay, so this is rated for 50 amperes. And so when we look over here at these conductors, we're going to start to determine whether or not the conductors are sized correctly. All right. So over here, we know they're all copper, so in that application, so even our SE cable in this case is copper. All right, so here's a 30, and we know this here is a 10 gauge. I can tell, I can actually see some of the orange sheathing, but if I didn't see that, I can tell by the size. I'm familiar with that size, as opposed to a 12 versus going up to, over the 10 goes up to an 8. I can tell that this is a 10 and it's on a 30, so that's okay. Here's another 30 and this is a 10. And here's another 30 and this is a 10. Okay, and so this happens to be a copper conductor here, and this happens to be a 6 gauge copper, and it's on a 60 amp. Again, if that application, it is based on the nameplate rating that says the maximum overcurrent protection, minimum circuit size. So we got that okay. Here's a 50 amp. We have a 6 copper on this as well, which is good, 55 amps. So we got it on a 50 amp breaker. We're good here. This is specific, so this follows the normal sizing rules under 240. Here we have a 40 amp, and it's got 8 gauge conductors to it, so we know that can easily handle 40 amperes, so we're good there. All of these breakers down here are 15 amps, and I can tell not just by the sheathing is white, but I also can tell by the size and ability of how freely they move that these are also a 14 gauge, so they're on a 15, so they're terminated okay. And over here we got the yellow on here, which is indicative of a 12 gauge non-metallic sheath cable, but to verify we can see the contrasting sizes between the 14 and the 12. And if anybody's ever worked with 12 a lot in kitchens and dining rooms and what have you, you get to know really quickly what a 12 gauge looks like. So here, these look like you can tell how stiff they are using a non-conductive probe. I kind of just touch them a little bit. I can tell what they are. So these are 12. So this looks like all of the breakers are terminated properly. Also, something to remember is you might have motors, you might have HVAC systems in here where it calls for a certain size overcurrent protected device, yet the actual branch circuit conductor might be smaller. And that's based on the nameplate. All right, so that's why we know this one's okay for the 60, because this is all based on the nameplate ratings and the circuit sizes. So we've looked at it here. And we don't have any issues, so all of them look good. We've looked at the terminations. We don't see any double taps in here. If we did, we'd call that out. That's where we're at now. So the next thing we want to do is we're going to finally, we're going to look at some of these labels a little bit. Okay, now we're on the left side of the cabinet, and we have an enclosure here that actually has some labels. Now, you're not always going to have this luxury when you're dealing with older panels, but this panel we do. And if you're looking here and you use your non-conductive probe, and this is the primary use for this non-conductive probe, is to be able to slide it in here and slowly a little bit pry away in order to be able to read these labels. And in this case right here, we can see that this load center is rated for 200 amps, and that's what we see located here. All right. We also notice that it says 240 volts. Okay, so we've got that right here. So we know that's a 240 volt, and we know it says it's a 40 circuit panel. It does say it's a type 1 enclosure. We do see that it's single phase because we have that marking right here, right above my finger, right there. We see it says 1 aught. One phase. That's a phase symbol. Excuse me. And we see it says a maximum main is a 200 amps. So that's going to tell you. You might find this in a panel that says 150 amps here, and it says maximum 150, and then you come over to the main breaker and it has a 200 in it. Obviously, that's something that you're going to know this is the weakest link. That means that right here, it says that this enclosure is rated for 150, so somebody has changed the main breaker. But here it says a maximum is 200. Now, if this is 200, I could have a 150 main breaker in here. That would be acceptable. Because the enclosure is rated for more. Again, but your weakest link is going to be this main breaker, which is only 150. Okay, so but here it gives us that information right here. Now, if you go down a little bit, as we kind of move down here, and I don't know how well you'll be able to see this, so let me try to slide down right there. And I'm trying to get the best angle I can so that you can actually see it. This is pretty important. Now, I'm going to try to hold these because I do want you to be able to see this. So I'm going to try to cheat a little bit here and get in here. All right, right here, it's going to tell you these are the ratings that are going to be for the size conductors that can go on the neutral bar, okay, the bus here, this bar. So this is going to tell you that sizes here that can be terminated. Now, up here, this is going to tell you here is the size of conductors that can go onto the main lugs. Okay, in this case, from a 4, let's see here, 4 all the way up to 250 kc mil. Whether it's aluminum or copper, it says right here. So 4 to 250 is acceptable for these main lugs up here. This table right here tells you the size of the conductors that will go onto the grounded terminal bus and equipment grounding bar, because that's here. And then down here is where you're going to get this little thing that says how many equipment grounding conductors that can share a terminal. Again, it says 2 12s or 2 14s of copper. And let's see, basically this one says, let me get my head in here, it says 2 14s or 2 12 coppers or 2 12 aluminums. Okay, so I could have, if I had aluminum conductors in here for branch circuits, that would be there so they could share. But that's going to let you know. You notice that it doesn't say that for the grounded conductors, only the equipment grounded conductor. Okay, so that's part of UL 67 and the listing of this enclosure here. So even if 408.41 says that you only have 1 conductor per terminal for the grounded conductor, it also is covered in this information here, and this has gone back many, many years for UL 67 and the panel manufacturers. Okay, so that's there. And here you have some torquing requirements as well for these torquing of the terminals and everything like that. It gives you some guidance on that for the electrician who's actually should be torquing all of these connections. Okay? So that's all that one pretty much gives you. Now, here we are at the other label that's on the right side of this cabinet. Here's what we got to earlier. It says suitable for use with, and you can't see here, it says 75 degrees C copper or aluminum main conductors. So again, the conductors coming in are rated at 75 degrees C, even though we know all of these non-metallic sheath cables are going to be rated at 60 degrees C for their application as far as ampacity. Now, we can use the 90 degree ampacity value for adjustment and corrections on non-metallic sheet cable when they're running in insulation or the number of current carrying conductors or bundling and what have you that are found in our requirements of 334.80. But just as a general rule, they're going to be limited to 60 degree column for 31015 B16 when it comes to ampacities. All right, so but the 75 applies to the main conductors. Again, branch circuit ratings again are going to be dealing with these terminals on these branch circuits are going to be rated here at 75 degrees C. Most all circuit breakers are. They might be 60/75 degrees C. None of these generally, especially in a residential application, are ever going to be rated 90 degrees C. Again, we use 90 degrees for adjustment and corrections only. So the one thing I want to point out in here is it says right here, it says this panel is suitable for use as service equipment when the service disconnecting, that's the main breaker, is installed. And of course, we have a main breaker. We are using it as service equipment. Okay, so that's the statement that tells us that. The other thing we want to start looking up here again, go up a little bit, is right there. All right, now what this is kind of unique for newer panels. You won't find this in a lot of the older panels, or you might find some old diagrams. And it should tell you where your main bonding jumper goes. And in this case, right here, it has a number 1. And if you take the number 1 and you look up here, you can't see it, but I'll bring it right here. It says that number 1 identifies with a box bonding when required. And of course, this being a main panel, it does require that main bonding jumper, again, to connect that neutral to the enclosure. Okay, and into all the equipment grounding conductors to that grounded conductor to the enclosure. So it's all tied together, which you don't want downstream, but you do want at a main panel. Here it tells you where to do it, and right there it says where that main bonding screw goes. Okay, now anywhere in here, some of the older ones you might have a main bonding jumper that can be anywhere on this side or anywhere, but in this panel it tells you exactly where it needs to be installed. So just be careful. And again, the screw in this case was green. But if it was prior to 1990, it might not be green. It might be of a silver finish. You just got to search for it on the panel. Take your time and look and see if you can find it to make sure. Now, at any case, you can't identify it or you can't really tell because some of the complexities of some of these panel boards, don't be afraid to defer it because we need to make sure of anything. We need to make sure that in a service panel, we have that main bonding jumper. And it might be a screw. It might be a Z-bar that connects from the bus over to the enclosure. Okay, it might be in a wire from the bus over to the enclosure. It could be in different ways, but you need to make sure that it's there. And in this case, it has a green screw, so we know that's the main bonding jumper. All right, so that's the information. And the last thing that I wanted to show on here is when we look up here, this is where you actually will find all the additional components that can be used in this cabinet. For example, when we talked about that equipment grounding bar, we have it available here. That can go in here. The screws are right back here. That's the model that you would look up in order to find the proper bar that goes in this panel if you're going to do a remote distribution panel where you have to separate the grounded conductors, which are the neutrals, and the equipment grounds. Okay, that's where you want to find the size. So this is where you get it. Right here, and it fits right in some screws that are located back here, back behind these wires. All right, so there, and it tells you anything else you need in here, the size and neutral lugs, and additional neutral lug, all of those information are right here. The main lug model numbers are all right here in case it's damaged and they have to replace it. All available. All of that can be replaced if it's damaged. So again, you're looking for any damaged lugs or anything like that. So that's kind of some legends that you'll find inside of a panel. Some are more detailed than others, but that's what you're kind of looking for there. All right, so I think we covered most of the things. If I left anything out, it's because I'm trying to cover as much as I can in about an hour or so. So that's all of the details we run into that. So the next step here is we're going to move out. We're going to actually now go out and look at the grounding system that we can see, and that's out at the meter. Now, lastly, before we leave, we want to recap. We know that this cabinet is rated for 200 amps because we saw that on the other legend. We know that the main breaker is 200. We know that the conductors are 2-aught, which in accordance with 31015B7 are okay for a 200 amp service. So everything else is indicative of a 200 amp service. Okay, now if you're sizing a service on an older panel, not all of these things might be available, or you might not be able to actually see the actual sizing on the conductors. So you've got to get used to these sizers. I knew these were a 2-aught copper by looking at them because I deal with it all day long. But you might not be able to, so you need to be aware of that. All right, so it looked like we looked at everything. So now let's go on and move out and look at the grounding scheme. Okay, we're out here at the meter. Now, one thing to remember about a meter when you're sizing a service is that you don't want to rely on it. Okay, sometimes they can take this meter socket and put it into different types of meter enclosures, and it might not be what you think it is. For example, this says CL200, which is very typical for a 200 amp service. However, I have seen CL200 meters installed in square 100 amp meter enclosures. So you don't want to rely on that. But since we've already have all the other details well known, now we're going to use that to help confirm the fact that we know that we have a 200 amp service. So in this case, this is a rectangular shaped meter, which is indicative of a 200 amp service. Now if this was square, then it would be indicative of a 100 amps meter, or maybe even a 125 depending on its age. If this was just a round one, then it would be typically either a 60 amp rated meter, or it might be even a 30 in an old style you'd see back in the 30s, where it had the meter itself and it had a little flap here, and the actual, you saw the open conductors coming in and then going out of it. That was typical with an old style. When they started to get to the 60, you actually came in with some raceways. So again, to kind of tell the difference in it. But I'm never going to use that as my final determination, okay? The meter is really just confirmation. So in this case, I know that it's rectangular. I'm looking at all the knockouts. They all are intact. There's no damage. There's no rusting. This is actually tight. It's actually sealed around it. It has up on the top, it has a hub cover. The hub is on there. I can actually feel the actual gasket. Everything looks good here. The meter tab's in place. The raceway here is not damaged. Everything looks good. It is kind of grayed out, but I do see sunlight resistant printed on here. It's very light. You're not going to be able to see it, but it is on here. But it is going to discolor out, but it doesn't show any deterioration. It looks in pretty good shape. The connection looks really good. It's not been stressed. Everything looks nice and snug. So as a home inspector, I'm not going to have any problem with this. It might have been nice to actually put some kind of securement here, from here down, probably within 3 feet. But you know what? It's pretty secure. As a home inspector, I'm not going to pretty much call it out. I don't see any damage to it. It looks in good shape. Okay. And a municipal guy, you got to remember that this is a service lateral, so this is technically outside of the scope of the National Electrical Code up to this point, whereas the actual service point is right here. Okay, of course that depends on where your transformer is on the property and whose control it's under. It might be service entrance conductors underground versus service laterals. If there's service entrance conductors underground, they're going to come under the NEC. If it's a service lateral, it's outside the scope of the NEC. The burial depths on that are governed by the National Electrical Safety Code, whereas 300.5 in that associated table is going to cover the burial depth for our conductors, service entrance conductors underground. So there's a difference in that. But as a home inspector, you're not going to see that anyway. We're just looking for any damage. So this looks okay. Everything looks fine. Now we know that we have a U for ground here, or a concrete case electrode. And a 4 gauge was run to that. And that's all the code requires to that sizing for that concrete case electrode. They didn't really need ground rods, but they added them in this house. So we're going to look for it and see how many they have and talk a little bit about the grounding electrodes when it comes to ground rods. Okay, as you can see, we have found the ground rod. It's right here next to where the 4 gauge comes out. So this is 4 gauge copper coming out, and it's actually connecting here to this actual acorn clamp that's on this ground rod here. Now again, this ground rod was not really necessary because they had a concrete encased electrode. However, they did use it, so when you use it, it does need to be installed correctly. Now, in this case, it was driven at an angle, which tells me they couldn't drive it straight down. It's required to be 8 foot in the ground. In this case, it's not all the way in the ground. Since it's not required, I'm not too often concerned about it. If I was a municipal inspector, I would make them drive it all the way down, flush with the earth, or down. The code actually says down below the frost line, but I really want to get it below the surface. They can cup out the dirt, if you will, so I can actually see it on inspection, and then they can cover it back up. This terminal right here, this lug, is actually rated for direct burial, so that is not an issue. They do actually have it installed correctly, whereas they have the grounding electrode conductor coming up through the back side of this acorn clamp and not on the screw side, so that's good that they have it that way. So in this case, it is driven at an angle. It's not required, so I wouldn't even worry about it as much as a home inspector. It is extra, it is additional there. It's certainly not going to hurt anything. So I'm just making sure. Now, if this was your only electrode, the National Electrical Code is going to require that we install now, under the 2014, 2 of these ground rods. Now, I can remove it down to 1 if I can show that that 1 electrode has a resistance to earth ground of 25 ohms or less. Now, if I can't show that, then I've got to install 2. Okay? For a home inspector, you might get an old home, then they only have 1. So you can recommend as a safety enhancement for them to add a 2nd. Or if you get to the aspect where they don't have any grounding electrode system, you most certainly want to call that out. And of course, a ground rod is probably one of the most easiest ones to add at a later date. So that's something you would call out if there wasn't any grounding electrode system here. Again, it's not to trip any breaker, it's not for fault current, it's simply for lightning and for surges, transients, allow the current, the voltage will, and all that to get to the point where it needs to go. So in lightning, it needs to get to the earth. So that's what this is for. Take it away from your electrical system. That's what you have the ground rod for. Don't get confused at driving ground rods at places and thinking that that's going to give you some return path for fault current, because that's not what ground rods, that's not what your grounding electrode system is designed for. Okay, that's what your equipment, grounding conductors and bonding jumpers and all that type of thing are designed for. All right, so this is installed okay. Don't have any problems with it. It is a proper acorn clamp. It is installed. Again, since there's already a concrete case electrode here, I'm not going to recommend a second one. This is good enough if they want to do it this way. Again, if this was the only one, then I would have to have them have two, at least 6 feet apart. Okay. There's some people, conventional theory believes they should be 8 feet apart, the same length of the rod, but the code says it only has to be 6 feet apart. All right. So that looks good. Now, also, you'll notice some terminations here. Now, these terminations onto the grounding electrode conductor are for the TV system, the antenna, or for other communication systems. Now, under the new code, you're required to have a separate termination called the intersystem termination point. So that intersystem bonding is required for all communication systems. It's not for use in order to make a connection to photovoltaic because it's convenient. It's only for communication systems. Okay, and that has to be mounted here on the outside at your service equipment, at your meter, those locations in order to be able to make those connections. Now, this was actually done before that was in the National Electrical Code, so they actually did make these connections, but they made them directly to the grounding electrode conductor. And if you're a home inspector, this is okay. I would accept this. Just check and make sure they're nice and tight and everything looks good, and that's fine. So that's the part that I want to just emphasize. These are going to go up to the TV cable system, to the data cable, the telephone, all those communication satellite dishes. They're required to make their connections, and so you have to provide them a place to do that. Prior to that intersystem bonding terminal requirement, then what you had to do was bring it over to the grounding electrode conductor, and that's what they did here. So this is all acceptable. I don't have any problem with this. I might recommend that this gets buried and tucked back, but it's not a requirement. We do want to protect this against physical damage. In this case, since this is exposed, it could be damaged, and in fact, this one I know is loose. So something has butted up against it and loosened it, so we'll need to tighten that back down. Other than that, I kind of tucked this away so it can't be exposed to any damage. So other than that, that's pretty much it for your grounding electrode system in this structure. Sorry I couldn't show you the UFO ground. That's also located inside the dwelling, and we did verify that as well earlier before we got into our inspection. Okay, remember earlier when we were talking about the outside unit and what's nameplates say? If you look at this nameplate here, you'll see that it says, right here, it says minimum circuit ampacity, okay, and that's 32 amps. Then it says the maximum fuse or circuit breaker rating is 50 amperes. Okay, so you'll notice that I have a 32 amp wire and I have a 50 amp rated overcurrent protected device. So I can have a 50 amp breaker protecting a conductor that has at least an ampacity of 32 amps. Okay, then I have no problem here in this application. So that's what your nameplate, this is what you follow to make sure that that's what's installed inside your panel. In that way, if you have a breaker that's on a conductor that looks like it's too small, and it's on something like this outdoor unit or an indoor air handler unit, that you go and look at the nameplate and you'll see that it is okay. This is acceptable and is allowed in the National Electrical Code. There's an initial startup surge and then it comes down to normal running current. And so if you follow this minimum and maximum here as put on the label, then you shouldn't have any problem, and that kind of gives you an idea of why that breaker might be larger when it's terminated onto a smaller conductor in the panel. But it's real important that you verify that you know that you're dealing with an HVAC system or a motor or what have you, and that's why it's important for that directory to be labeled properly so that you know how to identify this label with the circuit breakers that are inside the panel. Okay, with our inspection complete, the last thing we need to do is install the panel cover back on the cabinet, and we're ready to go on with the rest of our normal inspection. If you're doing electrical, you're going to check all the receptacles, light switches, all of that within the dwelling. If you're a municipal guy, you're done with the panel. Now you're going to do your walkthrough and do all your other inspections. Okay, so we're going to move on. So we're going to replace this cover, and then we'll get to that. Open up your cover so you can see it. Start up here. Kind of align it down so that it actually goes onto the main breaker first. Gets on there, and then make sure it's seated okay onto the panel. Look at your screws, and I'm going to install the first screw up the top. Put that in. Again, I'm holding the panel with my left arm while while I do it. I don't do it all the way tight so I can shuffle it around a little bit. So then I go to the left side and install that one. Okay. Alright, now I'm going to actually make sure everything looks good, everything's seated right in here. Line up those screw holes. Once it looks good, I'm going to shut the cover and I'm going to proceed to put all of the screws back into this panel. Making sure that I don't mar up the wall. Okay? So I'm installing them all in. Coming around, it doesn't matter what sequence I do here. We'll get it in the hole. And that's pretty much it. The cover's back on, everything looks good. Main breaker's seated all right, all the breakers are still in place. Checking them to make sure everything's good and nothing's catty-cornered. Anything looks good, everything looks well, and that's it. I want to thank you for watching our video on inspecting this electrical enclosure and panel cabinet. If you have any additional questions, feel free to visit us on our website at info@masterthenec.com. You can send us an email or visit masterthenec.com. And we also have a message board where you can actually post questions, watch our webinars, watch our podcasts, or listen to our podcasts. Do all that from our website. I want to thank you for joining me today. Again, if you have any questions, feel free to email us. Again, that is at info, that's I-N-F-O, @masterthenec.com. We look forward to hearing your questions. Until our next video, thanks for watching and God bless.